Hello and welcome to Lecture 5 of Gauss's Law in Phys 1204. In this video lecture we're going to see that when we want to know the E field due to a fairly highly symmetrical object, Gauss's law can get it far more easily than the ways we learned back in the electric fields unit of the course. So let's use Gauss's law to find the E field due to an infinite line, which we've already found in an earlier video lecture. But we're going to see that we get the same answer and that it's a lot easier. So first of all, a piece of terminology. I've already defined a surface, a closed surface around my line of charge. And we call these closed surfaces Gaussian surfaces. And so this is closed. It has end caps, and it's closed around the sides, and it's a cylinder. And the reason it's a cylinder is that we generally want to match the shape of our Gaussian surfaces to the symmetry of the charge distribution. Well, I already discussed the infinite line in an earlier video lecture, and we've seen that it has cylindrical symmetry. And so we want a cylindrical Gaussian surface. And the reason for that is that we now know that the E field points radially out from the line, if the line has a positive charge on it, everywhere. And that means that everywhere it passes through this cylinder, it passes through perpendicular to the sides. And note that it goes parallel to the edges. And we know that E fields going parallel to a surface result in no flux, right? They don't go through the surface. And so Gauss's law, which says that the Q inside our Gaussian surface over epsilon naught is the flux, which is defined as the closed integral E dot dA. But we can break that up into the integral over the sides, which is no longer a closed surface if we're just talking about the sides without the end caps, plus the integral over the ends. But we already know that the field is parallel to the ends, or you could say it's perpendicular to the dA vectors on the ends. So that results in a zero flux, and so this whole piece is gone. And then the other thing we know is that here the E field is parallel to the dA vectors, and so the dot product just results in a cos of 0, which is 1. And the E field is the same magnitude everywhere along this surface, and so I can just pull this out. I can pull the constant E field out and integrate over the area of the sides, and that just gives me the integral over dA over the sides is just the area of the sides. Well, the area of a cylinder, not counting end caps, is just its circumference, so 2 pi r, times its length. And now let's look at Q inside. Well, if this has a linear charge density lambda, then the Q inside is just the charge from here to here, which is just lambda L. And I'm practically done, because E is now just going to be, notice how the L's cancel. And so in the end, I get, after not an awful lot of work, just lambda over 2 pi epsilon naught r. Notice K is just 1 over 4 pi epsilon naught, and we've got a 1 over 2 pi epsilon naught here, so that's just 2K, and so this E field is 2K lambda over R. And so other than the fact that I'm calling the distance from the line R instead of X, this is exactly the result we got for an infinite line back in the E fields unit. Back in the electric fields unit of the course, we found the field due to an infinite plane of charge. However, it was really difficult. So difficult, in fact, that I put most of it into a supplementary lecture. Remember that what we had to do was first find the field due to a ring on the axis of the ring. Then we used that expression and integrated over a bunch of radii to get the field due to a disk. And then finally, we allowed the radius of the disk to go to infinity, and that gave us the expression for the strength of an E field due to an infinite plane of charge. That was a very long process, but as we're about to see, Gauss's law can get it for us very quickly. So here is our plane of charge, and we have to make some crucial symmetry arguments. So first of all, this plane of charge is going to have a uniform charge density sigma. And we know it has translational symmetry, and so does the field. And we also know from the reflection and rotation symmetry that the field has to be perpendicular to the plane everywhere. And the key now is to define a Gaussian surface. And we want a Gaussian surface so that these fields are going to be either parallel or perpendicular to every part, because that's what makes it easy. So the simplest thing to do is just to make a surface that is a box. And it has to include the charge. So the box is going to extend through the surface like this. And I'm going to say that it has gone the same distance above as it has below. And so by the reflection symmetry, I know that the E field strength through the top surface must be the same as the E field strength through the bottom surface. And I'm just going to call whatever that is E. And I'm going to define the area of the top and bottom surface as just A. And I'm going to call the area of all the sides A sides. And so now here is Gauss's law. And what I'm going to do, since I've got a Gaussian surface that's made out of flat planes, I'm going to break this up into integrals over each plane. So I'm going to integrate over the top, and over the bottom, and over the sides. And note, just a minor notational issue, that this was an integral over a whole closed surface, and so it's the integral sign with the circle on it, but these are now these flat planes, they're not closed surfaces, and so I haven't put the circles on. And the first thing to realize is that the A vectors sticking out of these sides are perpendicular to the E field, and so in the E dot dA we have a cos of 90 degrees, which is 0, and so this entire integral disappears. There's no flux through the sides. And second of all, the E field is parallel to the dA vectors out of the ends, and so there theta is 0, and so we have this usual situation that these are turning into EDAs with no vector symbols anymore. And I know the E field is the same everywhere on this surface and the same everywhere on this surface, and so these E's are constants. And so I have an E integral over the top dA and an E integral over the bottom. But those are just the areas of the top and bottom, which are just A. That's what I defined them as. And so overall, I get 2EA. So now let's look at the Q inside. Well, that is just the charge in this area here that's enclosed inside our surface. And that area is also A. And so that inside charge is just sigma A. And so we have Q in over epsilon naught, sigma A over epsilon naught equals 2EA. There's a common factor of A on both sides, and so it's gone. And so solving for E, I just get sigma over 2 epsilon naught. And remember that epsilon naught is 1 over 4 pi k. And so this is just 2 pi k sigma, which is what we got before, but it took us most of a video lecture to get it, and here we've got it in a few fairly easy lines. Let's do a slightly more complicated example. So here is a charge inside a hollow conducting sphere, and the sphere has an inner radius of A and an outer radius of B, and there's a total charge on the conducting sphere of plus 2q. This should remind you of something from an earlier video lecture, and we're going to find the E field everywhere. Well, there's one piece that we already know. We know that the field inside the conductor, so at radii between A and B, is 0. And our Gaussian surface that we put in there then has a 0 flux through it, and that tells us the total charge inside that Gaussian surface is 0. And so since there's a plus q in here, there must be minus q on the inner surface of this conducting sphere. And since the total charge on the conducting sphere is plus 2q, there must be plus 3q on the outside of our conducting sphere. So we already know one piece, which is that E is 0 for R between A and B. So let's now look at R less than A. So I'm going to grab myself a Gaussian surface that's nice and small, that fits inside the inner radius. And so I'm going to define my R as the radius of this sphere, and you can think of this as sort of a stretchy sphere. I'm letting this R vary as long as I keep it less than A. And so I know that the flux is equal to Q inside, which is just Q over epsilon naught. And that flux, from symmetry, I know, again, the E field is going to be radially outward everywhere, and it's going to be uniform magnitude on this sphere, and so going through the usual sort of steps that this integral, the E field is constant and pulls out, and so I'm left with just an integral over the sphere, and so I get EA is Q over epsilon naught, and E times A, that's 4 pi r squared, is Q over epsilon naught. And so E is just Q over 4 pi epsilon naught r squared, where r is less than A. And note that 1 over 4 pi epsilon naught is k, so we get kq over r squared. So now we know that E is 0 between A and B, and it's kq over r squared for r less than A, and all that's left is for us to do the case where r is greater than B. So let's do that. And it's going to go more or less the same way. Once again, the symmetry tells us that the E field is perpendicular to that sphere everywhere and the same magnitude everywhere on it. And so we're again going to have that phi E, the flux, is just EA, which is Q inside. Well, now careful. We've got plus Q and minus Q and plus 3Q. So overall, we've got 3Q over epsilon naught, and that A, again, is just 4 pi r squared. And so our E field outside, in other words, for r greater than B, is just 3Q over 4 pi epsilon naught r squared. And again, I can substitute that that is 3kq over r squared. And we now know E everywhere.